Recording.
Okay. Alright.
Is the camera all right?
Yeah, camera's fine. I mean, I can't mess with it any more than I did, so. Hilarious. I don't know, man. I'm recording locally. I'll upload it later. I've done that before. It's not the end of the world. Yep, good to go.
I should stream it to my laptop and I can stream it to...
Ooh, that's very sensitive. All right. Sorry for the late start. Yeah, it's not Space Drafts if we don't have a catastrophic technological problem right at the start of the show, or in between, or at the end. It's just a constant. So, for those of you who are new to Space Drafts, hello and welcome. My name is Nick. I am a fourth-year graduate student at the University of Arizona. You know what? I might as well start it at the very, very beginning. We are parked right next to a train line. So it is our tradition here at Space Drafts, whenever a speaker gets interrupted by a train, we raise our glasses and we toast the train with a hearty choo-choo! Thank you, Amtrak, for that perfect cue. Anyway, where was I? So, in case you are new to Space Drafts, usually we have two talks for you. Usually we have two talks for you every month, but this time we only have one for you, and after intermission we will have a little bit of astronomy trivia. Let me pull up my notes here. We're all out of sorts here. In that first talk, we will have also a trivia question, which will be your opportunity to win some merch over here. For our trivia competition after intermission, you will have the chance to, the grand prize winner, the first place person will receive a $30 Borderlands gift card. So stick around for that, for the trivia contest after intermission. Let's see. I did mention we have a merch table over here. We are selling merch, all Space Drafts themed merch. We can only accept cash for this merch, unfortunately. So if you don't have your cash on you, please come back next month and buy some merch over there if you want it. We also do accept donations. We are very grateful if you wish to donate to us. That helps us keep this show running. I already said the choo-choo thing, so without further ado, let me introduce our first speaker. Here to talk about dead planets around dead stars from Tucson's very own NSF NOIRLab, please welcome Dr. Laura Rogers.
Never had two things to juggle before, so we'll see how this goes. Okay, cool. Hi everyone, I'm Laura Rogers, and I'm going to be talking to you about dead planets around dead stars. So, without further ado, let's get going. So hopefully you all know that we are currently in the solar system. We are currently on planet Earth, which is the third planet from the sun. So you can see here, there we go. So, let's go back, that's a spoiler. Okay, we'll get the hang of this. So here we go, we've got the sun right here, and we are on planet Earth, which is the third planet from the sun. So in our inner region, we've got our rocky, small bodies. So we've got Mercury, Venus, Earth, and then Mars. And then a little bit further out, we've got our gas giants and our ice giants. But how do we actually know about what these planets are made from? And so what we do is we actually do things like measure the earthquake wave speed. So we can actually take these probes and have a look at earthquakes. And because waves travel at different speeds depending on the density of the material, you can actually work out the interior structure of different bodies. And this is mostly done for solid bodies, so our Earth and Mars. You can also do remote observations. I'm not getting the hang of it. Oh, there we go. You can also do remote observations, and so this happens when things like volcanic activity causes bits of material from the interior of your body to go into space, and you can measure the composition of planets from their interior based on what they're outgassing. And then you can also do something that's relatively basic but super powerful. You can measure the size of a planet, and then you can also weigh it. And from this you can work out the average density. And so you can work out that actually the inner systems, based on their size and their weight, these are very solid, and so they're made of things like rock. Whereas things that are a bit further out, these are gaseous, and they are a little bit less dense. But it wasn't actually until about the 1990s that we started to discover planets around other stars. So these are called exoplanets. And so far we've discovered about more than 5,800 planets around other stars. And so I'm just showing you a little plot here where we're just looking at the size and the mass of these bodies. And this is really like the best thing that we can do for whole exoplanets if we really want to understand their interior and what they're made from. Because something that really drives us as astronomers is trying to work out, like, what are these planets made from? Like, could we stand on them? Are they solid? If we were to jump on them, would we go very high? Would we not? Would we not even be able to stand on them at all? And if we were lucky enough to stand on them, could we breathe the air? And so really the best thing we can do with these is look at the radius and the mass. So just to break it down for you, here we're looking at the radius. So if you're in this part of the plot, you're very big, but you're not particularly heavy. And so most of the time, things that will lie up in this region are going to be quite gaseous. Whereas if you're down here and you've got a really small size, but you're very heavy, then you're probably made of something pretty damn solid, like potentially iron. And so if we look at where our things in our solar system are on this plot, so Jupiter is up here, and this is where gas giants tend to sit. Whereas down here, this is where terrestrial planets like the Earth sit. And so if you're interested in habitability and looking for exoplanets that you could probably stand on, then you're probably interested in looking down here. But as I said, when we're measuring the size and the mass to get the rough density, this really is the best thing that you can do with whole exoplanets. But I'm really interested in actually getting inside them and learning about the nitty-gritty, like what elements and what things make up the interiors of these exoplanets. So in the most ideal world, I would take a planet, I would hammer it down into dust, and I would put it into a really cool machine called a mass spectrometer. And so if I were to take the Earth, luckily I'm not going to do this, we're still going to be standing on the Earth at the end, but if I were to take the Earth, hammer it into dust, and then put it into a mass spectrometer, this is what I would find. So I would find that the Earth is made mostly of iron, 35% iron, 30% oxygen, 15% silicon, and 13% magnesium, plus a number of other elements. And these elements are all crucial for us to survive on Earth here. But we really want to get this kind of understanding of exoplanetary material. I can't go and hammer down exoplanets, but what I can do is use dead planets around dead stars. So I'm going to tell you a little bit more. What is a dead star? So this may immediately come to mind when you think of a dead star. This is a Death Star from Star Wars, obviously. But actually, when I'm talking about dead stars, I'm talking about white dwarf stars. So white dwarfs are actually dead stars because when a star similar to our sun goes through its life cycle, it will end its life as a white dwarf. So here I'm just showing you the life cycle of some stars. And so stars will form out of a cloud of gas and dust. It will go onto its lovely main sequence phase. This is just where our sun is, where it's burning its nuclear fuel and having a nice jolly time. But at some point it's sort of, it's burnt through its fuel, we all get tired and we want to give up. So that's what just happens to these stars. And they go through their red giant phase. And then they expel their material in a planetary nebula. And then they leave behind the core of their star. And this is a white dwarf star. If we had a more massive star, it would go through a completely different evolution. And it would end up being either a neutron star or a black hole. They're interesting, but we're going to ignore them for now, because we really care about these white dwarf stars. So white dwarfs are small and they're also massive. So if we just kind of try and extrapolate the size of this sun, this is actually to ratio scale of the sun and what the sun would be as a white dwarf. So they really are very, very small. So you will pack about the mass of the sun into the radius of the Earth. So they'll have a really high density. And because of that, you would only expect to have the lightest possible elements on the outside, so the lightest gases like hydrogen and helium, and anything else will just sink out to the core super quickly. Kind of like when you're throwing stones into a lake, like anything heavy will just sink out, you won't see it. So this is the closest white dwarf to us. And this isn't the trivia question, but does anyone want to point out where the white dwarf is? Well, okay, fine, very funny. It is on the screen. Is it the big one on the left or the small one on the right?
On the right.
Yes, it's the small one on the right. This is Sirius. So this is a binary system which contains a main sequence star, which is Sirius A, and then the white dwarf, which is Sirius B. And this white dwarf, the white dwarfs are incredibly small, but I think it really puts into perspective the size difference between a main sequence star and a white dwarf. And something else you'll notice is that the white dwarf is actually super, super blue. And why is that happening? Are we going to cheers? Yeah! I mean, I don't know, maybe it's going to come closer. But why does the white dwarf appear so blue on the sky? So to answer this question, we have to go to the electromagnetic spectrum, which is basically looking at your energy as a function of wavelength. So things that are super high energy have a really short wavelength, and that's the gamma rays over here. And then the wavelength gets longer, and you get all the way down to radio waves. We can actually only interact or really see the visible part of the spectrum, and that's just this tiny little region here. And so everything has basically a peak wavelength, which is like the best wavelength that you emit at. You emit most of your energy at that particular wavelength in the electromagnetic spectrum. And so us as humans, we tend to emit in the infrared, which is why we're quite hot. Maybe we cheers there. It did get closer and it did get louder. So as humans, we emit most of our waves in the infrared. The sun actually has a peak wavelength of about 600 nanometers, and that's why it appears so yellow in the sky. But white dwarfs, on the other hand, they are really hot, and so they give off a much hotter energy, and therefore they appear around this region of the spectrum. And so their peak wavelength is in the blue or towards the purple, and that's why they appear so blue in the sky. What about a dead planet? We've spoken about dead stars. So sadly, it's not like Alderaan, they don't get blown up, but they become tidally disrupted. So you're gonna have to bear with my PowerPoint skills here. So white dwarfs have a tidal disruption radius that's quite far outside of them. And what this means is because the white dwarfs are so dense, if anything gets anywhere close to the white dwarf, it just can't hold itself together anymore, it just has to be torn apart. And again, everything has a tidal disruption radius, but the sun's tidal disruption radius is like within its envelope, so this doesn't happen. But because white dwarfs are super small and super dense, this happens. So you get this kind of chunk of planetary material, it goes in, it hits a tidal disruption radius, and it disintegrates. And then it will fall onto the white dwarf. If I say accrete, this is what this means. It accretes or it falls on to the white dwarf. And so here is just a nice little animation which is showing you what is happening. So you have a chunk of planetary material that's being flung towards the white dwarf. It hits a tidal disruption radius where it's ripped apart, and it forms this disk. And this disk is actually observable. We've observed about 100 white dwarfs that have disks. So this material spirals in, it gets hot, and then it accretes onto the atmosphere of the white dwarf. And this is where I take a telescope and I look at it, and then I try and work out what the composition of this material is based on my data. So, why is my title about dead planets and dead stars? Well, the dead stars, which are these white dwarfs, that swallow dead planets, which are tidally disrupted planetesimals, asteroids, or fragments of a planet that fall onto the white dwarf and pollute the atmosphere. It doesn't make for as catchier of a title, but hopefully you understand why that's the case. And so we call these white dwarfs polluted white dwarfs. So actually pollution can be a good thing. Okay, so how do we go about actually studying or even finding polluted white dwarfs? Well, we're going to go back to our electromagnetic spectrum. And what we do is we do spectroscopy. So we're looking at the white dwarf, so we're getting the light from the white dwarf, and we're splitting it up into its constituent wavelengths. And so we mostly will do this around the visible and the ultraviolet for white dwarfs, because this is where most of this is their peak, this is where most of their light is emitting at. And so when I look at what we call a spectrum of a white dwarf, there are going to be very particular points at which there's some light that's missing. And that's because if there's something like iron in the atmosphere of this white dwarf, it's going to absorb some of the light at very particular wavelengths. But I'm smart and I know exactly what wavelengths iron is going to absorb at. So I can look at a spectrum and I will know if iron is there. And by how much light is being blocked from the spectrum, I also know exactly how much iron there is. But there's not just iron, there's many other elements as well. And so you can really build up again understanding of what elements are in this planetary material that's fallen onto my white dwarf and how much of it as well. So I thought I would just show you kind of what on earth I'm talking about. So this is just an example of a spectrum. You can really ignore the axis. This is just the brightness versus the wavelength. And this is Sirius B. This is the closest white dwarf to us. Sadly, it is not a polluted white dwarf. But what you can actually see is that the white dwarf is absorbing light at very particular wavelengths. And these are the hydrogen features. So this is showing you that these are the hydrogen fingerprints in the spectrum of this white dwarf. But if you add metals, and so again here we've got the hydrogen, but there are additional lines of metals. So this is magnesium here, this is calcium, this is a little iron block there, and a big calcium line here. And I know exactly which element is absorbing where, and so I know just from the spectrum that this white dwarf is accreting or swallowing material that is rich in iron, magnesium and calcium. And so I can reconstruct the composition of this planetary body. So, quick trivia question then. How do astronomers study what's polluting a white dwarf? Let's see if you've been listening. A, by measuring the white dwarf's brightness with their eyes. B, by analysing the starlight using spectroscopy to find chemical fingerprints of elements. Or C, by sending a probe to collect samples from the star's surface. Do we like pick someone? I'm not sure, is it? But in general, yeah, all good? Okay, well, good job everyone who shouted out B, that is correct. Just going through them. So A, by measuring the white dwarf's brightness, that is what we do, but we actually can't do that with our eyes. We can't see any white dwarfs with the naked eye. We do look at the starlight using spectroscopy to find the chemical fingerprints of elements. But we sadly can't send probes to collect samples from the star's surface. I would be very much gone if I tried to do that, and I don't think anyone would understand what I was trying to get back. So yeah, the answer to this is B. So my favourite fact about polluted white dwarfs is actually that the first polluted white dwarf was discovered in 1917 by Van Manen. And so he was just trying to look at kind of fun stars that are moving really quickly in the sky and discovered a really strange star. And so he actually classified it as an F0 type star, which is not that dissimilar to the Sun, but it was very much had a question mark over it. But we now know that this is actually a polluted white dwarf. And so the reason I think it's fun is because it wasn't until the 1990s that the first exoplanet was discovered. But actually our field kind of beat that by like many decades, because we found the first polluted white dwarf in 1917. So I think we should have got the Nobel Prize. Yeah? Anyone? Yeah? Okay. Yeah, we should have. Sadly we did not, and we probably won't. But, you know, we can dream. So I'm just going to tell you about a couple of the fun things that we do when we find polluted white dwarfs and what sort of things we can learn about. So firstly, I'm showing you the elements that we've measured just on a periodic table. And so far we've actually discovered 23 different elements in the atmospheres of these white dwarfs that are coming from planetary material. And so we're at the point where we can really start to build a good picture of the composition of these exoplanets. And so if you go back to our kind of mass spectrometer and we broke it down and we found our little pie chart with what was in the Earth, well, we really can actually do that for exoplanetary material. And I think it's important to talk about water, because astronomers love trying to find water. And I think we always will, because water's super important for us, especially in the desert. But we're made of 70% water, and we need water. And so water, let's try and find some. And we can actually look for water that is basically polluting these white dwarfs. And so we have to do this in a very basic way where we're essentially like counting atoms. But we go to our white dwarf and we observe it with some amazing telescopes. For example, Hubble, or the Very Large Telescope, which is really well named. And then we measure all of the different elements that are in its spectrum. And then we basically build a rock. So we have all of our different elements and we just, in our heads, put it together and we try and say, well, how much oxygen do we have? And we know that water has the symbols H2O, so you need 2 hydrogen for every single oxygen. And so if you've got lots of oxygen left over once you've built your rock, then you'll probably have something that's quite water rich. And so if you don't have much oxygen, you're up here, you've built a nice dry rock. And if you do, then you've got a water-rich body. And what we're finding is actually the majority of the time we're just seeing nice dry rocks just accreting onto white dwarfs. Very fun. But actually about 10 times we've seen really water-rich planetary material accreting onto these white dwarfs. So we are finding that water is prevalent out there, which I think is pretty exciting. And another thing we can do is actually something more to do with the interior of bodies. So we're asking this question, well, do exoplanets have cores and mantles? And so, well, how does that happen? So if you have a rock and you heat it up, it goes through this process called differentiation. And what that means is all of your heavy elements sink down to the core of your body, and all of the lighter elements stay in the outer regions. And so you get a core, a mantle, and a crust. And so this is exactly what we have on the Earth. We've got a lovely core, and we've got a mantle, and we've got a crust. And this is really important for things like recycling of elements. Like, we probably wouldn't be here if it wasn't for the fact that we were sat on a differentiated body. And so we really want to look at whether this is actually happening in exoplanetary systems. And so we know that if we had any core material, you're going to be having like a party with iron and with nickel and chromium, whereas if you were in the mantle, you're going to be having a party with things like silicon and magnesium and calcium. And so when we're looking at the composition of the planetary material that's in a white dwarf, we therefore know, depending on what elements we see, whether it's like a core-rich party or a mantle-rich party. But it's difficult because actually we can't tell the difference between if someone were to just like chuck this one on a white dwarf or chuck this one on a white dwarf, because we're only seeing like the bulk composition. And so the only way that we could look at a white dwarf and see something that's core-rich or mantle-rich is if it's gone through a load of collisions and you've got something that's kind of mantle-rich or core-rich or even crust-rich. And so these then have to accrete onto the white dwarf. But it's possible, and we've actually observed these kind of things out there in white dwarfs. So we've seen things that are really rich in this kind of like iron, nickel, and chromium, and we've also seen things that are really rich in magnesium and silicon and all of the good mantle stuff. And we've even seen fragments of crust too. So this process called differentiation that's super important for life on Earth is actually happening out there too, which I think is pretty neat. So, hopefully I've convinced you that studying dead planets around dead stars can really tell us about the composition of exoplanets. We've already characterized more than 100 white dwarfs that are eating planetary material. And so we found some white dwarfs that are accreting material that's super rich in water, and we've also found examples of chunks of core, mantle, and crust material. But I think the thing that's kind of nice is that actually, when we look at it as a whole, most white dwarfs are accreting material that's really similar to the Earth. And so Earth-like material actually seems pretty commonplace in the galaxy, so I don't think we're that special after all. Anyway, thank you very much, and I'm happy to take any questions. That's a great question. Oh yes, can you tell us why iron is so abundant, and do we ever see any heavier elements from the spectroscopy? Is that right? Yeah? Iron is really abundant for a number of reasons, but there's this, there's basically this energy thing, where iron is going to be the peak element in terms of like how energy works. And so kind of everything sort of will tend towards being at iron, and then it's really difficult to kind of, in an energy balanced way, to produce things that are heavier and heavier. So that's really why iron is so abundant. But we have seen things that are just a little bit heavier than iron, but we never go anything kind of too crazy, and probably because one, it's very difficult to observe, but also because it's going to be so much less abundant, we're not really going to see that big lines. So I really think we're probably limited by that. Maybe we need a very, 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 very large telescope. That's a great question. So the question is basically, how do planets survive to the white dwarf phase? And the short answer is some don't. Actually, if we think about our own solar system, probably the inner regions are not going to survive. The jury is still out as to whether the Earth will survive through the red giant phase and into the white dwarf phase. And so actually we're going to lose a lot of the inner system. But what happens is you get expansion, and so the outer regions do actually survive. And so you can get, like, in our system, we probably still get the belts and the giant planets, and probably Mars, that will survive to the white dwarf phase. But it's super chaotic, and that's why stuff gets flung towards the white dwarf in the white dwarf phase. Can you shout back, sorry? How do you know if a white dwarf is polluted or not? Okay, so I mean, you probably heard that with me doing that, but how do you know if a white dwarf is polluted or not? So this is entirely based on the spectra. And so I mentioned earlier that the white dwarfs are so dense, so you would only expect to see either hydrogen or helium in the outer regions of the white dwarf. And so if you see anything else there, then there has to be some kind of external source that is causing there to be something there. Otherwise it will just sink out and you wouldn't see it. And so when I look at a white dwarf and I see things like iron, magnesium, and calcium, I know it's polluted because it's the only possible explanation for that material to be there. That's a great question as well. So this is what percentage of white dwarfs are polluted and not. So roughly speaking, we're really looking at about 30% of white dwarfs are polluted. And it depends because we know of at least 1,700, and then there are statistical studies that are done to try and put percentages on it. And so we're really looking at about 30% that really look to be polluted. Last question, who, I think that person put their hand up first, I'm so sorry. You know, oh, okay, so the question is, when you get a planetesimal that comes in and it gets tidally disrupted and it's in a disk, how long does it take to accrete? If I knew that, I probably would be a bit richer than I am now. This really is quite an open question, and we're debating it a lot, actually. So some people think that you can have material that moves in really quickly, so over timescales of sort of 10 to 100 years. But other people are saying a lot longer, kind of 10 to the 5, 10 to the 10, you know, a really, really long time in terms of years. But there's a space telescope that's gone up called JWST, James Webb Space Telescope. And so I'm hoping that we'll be able to do some really interesting studies on that, and I think that will really help us to probe these kind of things, but jury's still out at the moment. Cool, thank you.
All right, thank you again, Laura. Before we break for intermission, I have a very quick announcement. Over here, off to your left, we have some representatives from the Tucson Symphony Orchestra. They are here to promote the upcoming event, Star Wars The Force Awakens in Concert. That is a concert by our very own TSO. It is running on May 17th and 18th at Linda Ronstadt Music Hall, right across downtown. Over there they have a theremin among a couple other sci-fi instruments for you to check out. And if you would like to purchase tickets for the concert, you can also buy them over there with them. So please go check that out as we take 20 minutes for intermission. It is currently 8:10. So intermission, head over there for some orchestra stuff, head over here for some merch, and we'll see you back here right at 8:30. Don't forget to tip your bartender. See you then.